Hi, good morning, everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, working at Nagarjuna Government Degree College, Nalgonda. We are we have been discussing coordination chemistry chapter for BSc second year third semester chemistry students from last week. So far, we have discussed about a short recap. What are coordination compounds, how they differ from double salts, what are the terminology we use in this chapter, that is uh, that is those are those are just wait. Okay, I am switching off my phone first. Okay, so uh, what are coordination complexes, what is a complex cation, what is a complex anion, and what is a central metal atom, what are ligands, how they classify, like classification of ligands, and including monodentate, bidentate, polydentate, and chelating ligands, ambidentate ligands. All these we discussed terms. Then we discussed IUPAC nomenclature of coordination compounds. By using this IUPAC set of rules, we have given names to different compounds, and from the name of the compound we have to write the formula of the complex. We have learned all these things, followed by Werner theory of coordination compounds, then drawbacks of Werner theory, followed by Sidgwick electronic interpretation of coordination compound, electronic interpretation, effective atomic number, calculation of effective atomic number to different compounds. Then we have discussed valency bond theory, especially valency bond theory, important postulates, and using this valency bond theory we have explained different coordination compounds, tetrahedral complexes, square planar complexes, and octahedral complexes. By taking more examples, we have discussed different geometries of different coordination compounds, and finally we have discussed some setbacks, drawbacks of this valency bond theory, which is proposed by Pauling. Pauling. Then in this class, in this session, we discuss isomerism in coordination compounds. So what is an isomerism? What is the classification of isomerism? How many types of isomerism we discuss in this chapter? And we will discuss some type of structural isomers in this session. So we are going to start today's class. Okay. So what is in this class, what is isomerism, definition of isomerism, and different examples for isomers, and then followed by classification of isomerism, and each type of isomerism is explained by taking at least one or two examples each. So I am going to today's slide. These are the different slides for all these things are discussed. Okay, okay, coming. Okay, this is isomerism in coordination compounds. This is today's chapter. Then, so what is isomerism? We know in the organic chemistry or in the previous classes we defined isomerism well. There are some compounds which are having same molecular formula, but they differ in properties, maybe chemical or physical, some optical, whatever it may be. So having same molecular formula, but different compounds of different properties. This phenomena is called isomerism. Those compounds which differ in properties are called isomerism. Isomers. Compounds which differ in properties having same formula are called isomers. The property or the phenomena is called isomerism. The different properties may be chemical or physical or optical regarding rotation of plane polarized light. So all these things. So these are isomers. Iso means same. Iso means same, having same molecular formula, exhibiting different properties. The compounds or molecules are called isomers. The phenomena is called isomerism. So we are specially focusing this isomerism relating to coordination compounds, complexes. Okay. So this is a classification of isomerism in coordination compounds. Generally, these isomers are broadly isomerism is broadly classified into two types: structural isomerism and stereoisomerism. So isomerism is based on bonding connectivity. So bonding connectivity is same, but properties are different. A structural isomerism. Okay, bonding activity is different. Bonding activity is different. Structural. Bonding activity is same, but there are different properties comes under stereoisomerism. So in general, isomerism broadly two types: structural isomerism and stereoisomerism. So what is structural isomerism? Compounds having same molecular formula but difference in properties due to difference in bonding connectivity. So bonding connectivity is changing. Even though two compounds are having same molecular formula, due to difference in bonding connectivity or structure or arrangement of atoms, there is some difference between difference in properties of compounds. So those compounds are called structural isomers. The phenomena is called structural isomerism. Coming to stereoisomerism, the compounds having same molecular formula, same bonding connectivity, but differing in arrangement of atoms around the space of a central atom. So this is in this case bonding connectivity is same in both compounds, but orientation of atoms around the space is differing. That's why sterically they are different. Stereomeric arrangement is different. So that's why those are called stereoisomers. Stereo means space. So space in the arrangements of atoms around the space is differing with the same bonding connectivity. So that's why these are stereoisomers. The phenomena is called stereoisomerism. So coming to structural isomerism, we have 5 types in our syllabus in coordination compounds. One is ionization isomerism, 2 is hydrate isomerism, 3 is coordination isomerism, 4th is ligand isomerism, 5th one is coordination position isomerism. So all these 5 types comes under structural isomerism. Structural isomers. Coming to stereoisomerism, these are further divided into 2 types: optical isomerism, geometrical isomerism. So we'll discuss these stereoisomers in the next class. Today we will discuss in detail about this structural isomerism. So isomers are 2 types in general, in broad. structural isomerism, structural isomers and stereoisomers. So, okay, so we'll discuss structural isomers in detail. Okay, what is a structural isomerism? Just now I discussed, I already explained. It is displayed by compounds that have different ligands within their coordination spheres. We know what is a coordination compound, what is a central metal atom, what is a coordination zone or sphere we discussed. In the coordination spheres, ligands may be changed. Formula, two compounds having same formula but different in bonds with central metal atom or ligands. So structurally they are different even though they are having same molecular formula. So that's why this is called structural isomerism. Those are called structural isomers. These isomers have same molecular formula but different structural arrangement of atoms or groups of atoms around the central metal atom. This is a definition for structural isomers and structural isomerism. Okay. Okay. So types of structural isomerism. So this is only for coordination compounds, not for all. So structural isomerism in this chapter, in these compounds, further 5 types. We already we discussed, we learned these types of, in the previous slide. One is a ionization isomerism. Second is a hydrate isomerism. Third is coordination isomerism and linkage isomerism. Finally, coordination position isomerism. So these are different structural isomers we are going to discuss in this session. Okay, next slide. Okay, so in the first we'll discuss about ionization isomerism. So in the name itself it is understood when two compounds having same formula but when they dissolved in a solvent or in aqueous solution they are giving different ions. So ions are different, though having compounds having same formula, properties are changing. They are exhibiting different properties due to different ions present in solution. That is the ionization isomerism. So ionization valency, the valency satisfied, the primary valency, the groups which are satisfying primary valency are changing. That is important. We will discuss with example. So this is ionization isomerism. Those proper compounds are called ionization isomers. Compounds having same molecular formula but they are exhibiting different properties due to having different ions in solution. That is, the ions which are satisfying primary valency are changing in these two compounds, pair of compounds. That's why those are called ionization isomers. For example, if you take one example, if you take this compound, these two are classified as defined as ionization isomers. So what way you see both compounds are having same formula, one cobalt atom, ammonia molecules ligands, ammonia molecules 4, 2, 3, 4, 5, in each case 5. One is one bromide and one sulfate. This is a common formula, molecular formula of these two compounds, CO NH3 5 Br SO4. So both are having same molecular formula. But when we dissolve this compound in water, it is giving sulfate as in solution. Whereas this compound, when dissolved in this compound water, it is giving bromide in ion in a solution. So the compound's color also changing. See, this compound exists in violet color, whereas this compound exists in red color, exhibiting red color. So compounds both are having same formula, one cobalt atom, 5 ammonia molecules, one bromide ion and one sulfate ion. Both are having same formula, same chemical composition. Okay, but properties are changing. First compound is existing in violet color, second compound existing in red color. Further, these aqueous solutions are giving different properties. Why? This, when we dissolve this compound, we are getting sulfate as a free ion. We know that sulfite gives a white precipitate with barium chloride, whereas this compound doesn't give test with the Ag silver, that is barium chloride. Why? This compound is not giving sulfate free ion, as it is involved in taking part in coordination sphere. So you see carefully, if you observe carefully, in this complex, sulfate is out of the sphere. In this complex, sulfate is within the coordination sphere. In other words, in this compound, bromide in coordination sphere. In this, bromide is out of the coordination sphere. It's a counter ion. Bromide is counter ion in the second instance, in second example, whereas sulfate is a counter ion in the first example, first molecule. So that's why properties are changing. This compound, when the solution, it is giving white precipitate with the barium chloride. This compound doesn't giving white precipitate with the barium chloride. Whereas this compound is giving with a silver nitrate test, whereas with a yellow PPT, this is not giving that yellow PPT with the silver nitrate, pale yellow PPT. So because of lacking bromide ion, we know that bromide is a free bromide ions in aqueous solution. They give pale yellow PPT with the silver nitrate, whereas sulfate doesn't give this test. So these are the differences of these two compounds, one compound, two compound. So that's why these two compounds are called as ionization isomers. That's why this phenomena is called ionization isomerism. I'll explain once again. Ionization isomers are the isomers having same molecular formula, same chemical composition, but they differ in properties due to different in ions in aqueous solution. So this compound is giving sulfate test, this is not giving sulfate test. It is understood that the sulfate is out of the coordination sphere in this compound, whereas in this compound sulfate is in coordination. As we know that coordination compounds, when they dissolve in water or any other solvent, complex ion is retains their property. Only counter ions they are given to the solution, they are responsible for different properties. Complex ion as such, it has some own properties. It doesn't lose its properties when they dissolve in solution. That means they retain their property. So that means sulfate ion doesn't give test in this compound. Why? Because sulfate is involved in coordination zone, coordination sphere. It is linked with cobalt through coordinate bond. That's why this is not going to dissociate. That's why properties are changing. This is example for ionization isomerism. Okay, you see once again it is explained in this slide also. So this is in this compound sulfate is out of the coordinate sphere. In this compound sulfate is within the coordinate sphere. So this in this bromide is linked to directly through coordination bond to the cobalt, whereas this bromide is a free as a counter ion. So this is come to the water in the aqueous solution. This doesn't come. That's why those two compounds are having different properties due to this difference in ionization. So that once again I try to explain. In this complex, this primary valency of cobalt is satisfied by sulfate ions. In this complex, cobalt ion primary valency, we know 2, it is satisfied by bromide ions. Okay, that's why 2 bromide ions, it should be 2. Okay, that's it. This is something about ionization isomerism. Next slide. So you see one more example. So you see in this example, so this compound, name of the compound we shall try to give the IUPAC name is a nitrate compound, nitrite compound. In nitrite, in the first case, nitrate is a counter ion. In the second case, bromide is a counter ion. So bromide is a nitrite. Okay, what is the name? Nitrite is NO2 minus, cover this why it's a plus. So Br is minus, that's why it is a plus 2, platinum plus 2 state. Okay, platinum is plus 2 state. So name of the compound is bromo. first amine. Why? Because A is there, no. Triamine, bromo, platinum, 2 nitrite. Name of the compound, IUPAC name. So coming to the next second compound, you see this is a bromide. Br is there. Bromide Br minus, that's why it's a +1 complex as a cationic complex. So nitro is -1. So the platinum charge is +2. So first you have to tell bromo. No bromo. Nitro is there, amine is there. Triamine, nitrito or nitro, platinum 2 bromide. So this is the name of the IUPAC name of the compound. You see, you observe carefully what is happening. So when we dissolve in water, it is giving NO2 minus ions. This compound gives bromide ions in the aqueous solution. You see, that's why you are studying, classifying this set of compounds as ionization isomers. Why? Because this just gives for nitrate, this gives with AgNO3. So this compound doesn't give with a test with AgNO3. Why? In this case, this bromide is involved in coordination sphere. That is not comes as a free ion. That's why this compound doesn't give test with AgNO3, whereas this compound gives Ag on the test. That's why. So even though two compounds having same formula, one is giving test for bromide, another is not giving test for bromide with AgNO3. So that's why, this is the reason. That's why we can classify these two compounds as ionization isomers, as in the first instance platinum is satisfying its valency through nitrate NO2 minus ion, whereas in the second example, second compound, platinum is satisfying its primary valency with bromide ions. That is the difference. So when they dissolve in water, bromide ions are, second compound is giving test for bromide, first compound is doesn't give and responding with AgNO3 test. That's why these are also classified as ionization isomers. Okay, I think you understood the first one. We are discussing structural isomerism in coordination compounds. In structural isomerism, we have 5 types. Out of 5 types, we discussed one, that is ionization isomerism. Second is hydrate isomerism. Okay, so what is hydrate isomerism? What are different examples? When the name itself, it is understood, hydrate means water. So difference in water molecules in the coordinate zone. That means the number of water molecules in the coordinate sphere changes. So compounds having same molecular formula, but the water molecules around the central metal atom or ion is changing. In the coordinate sphere, water molecules are changing. That's why this type of isomerism is called hydrate isomerism. Those are called hydrate isomers. So difference in water molecules around the central atom, properties are changing. You see one example. For example, CrCl3 compounds with same formula, CrCl3 6H2O. So 3 compounds are possible. One is existing in green color, second is blue-green color, and third one is purple color. So different physical property, color property is changing, color is changed. So these are 3 are different color, exhibiting different colors. Why? So once again, one more thing, when we heat this compound, 2 water molecules lost on dehydration. If you heat this compound, if only 1 water molecule is lost on dehydration. If you heat this so much temperature, this compound doesn't undergo dehydration. So this is one more difference. So one difference is color. First compound existing in green color, second compound in blue-green, third compound is purple, even though these 3 compounds having similar molecular formula. This is one difference. So second difference, this is on heating with the sulfuric acid or phosphorus pentoxide, we know that there is a dehydrating, those are dehydrating agents. Dehydrating agents, they remove water molecules from compounds wherever possible. So even though this compound is having water molecules in the coordination zone, these water molecules doesn't lose in dehydration process. That's why the number of water molecules participating in dehydration reaction is changing. In this in this case, only 1, 2, 3, 4 water molecules are involved in coordination zone sphere. In this case, 1, 2, 3, 4, 5. In this case, all water molecules are present in coordination zone. That's why these are not eliminated as water molecules when we heat this compound. So this is giving test for 3 chlorides. This is giving test for only 2 chlorides. This is giving test for only 1 chloride. That means 1 mole of AgClPPT is forms with excess of AgNO3. So the second example giving 2 moles of AgClPPT, the white curd is precipitate with AgNO3, 2 moles with excess AgNO3. Whereas this one is giving more precipitate with silver nitrate. So this is also one difference. So color is changing. On dehydration, number of water molecules undergoing dehydration is changing, and reaction with AgNO3 giving amount of white precipitate is also changing. So that's why this is happening is the number of water molecules are changing from compound to compound. In the first example, we have 4 water molecules coordinate to central metal chromium ion. In the second case, 5 water molecules are surrounded. In the third case, 6 water molecules are surrounded. So that's why no water molecule left, and that's why it is not participating in dehydration reaction. So this is about hydrate isomerism. I repeat, hydrate isomerism exists in compound in which there is a change in coordinating water molecules with the central metal atom is changing. Okay, so due to difference in water molecules, coordinated water molecules, the properties are changing. That is expression about hydrate isomerism. Coming to coordination isomerism. You see, coordination isomerism, compounds having same formula. So all these are structural isomerism. We are discussing only structural isomerism. So compounds having same formula, okay, different bonding connectivity. You see this example, we have this is one okay, sorry, okay. You see, this is one compound, this is one another isomer. These two different compounds having same formula. How? In these two compounds we have cobalt and chromium. So one cobalt is there, one cobalt is here. In this compound also we have chromium, we have chromium. In this compound we have six ammonia molecules. In this also we have 6 ammonia molecules. In this case we have 6 cyanide ions. In this also the 6 cyanide ligands. So chromium, cobalt, 6 ammonia molecules, 6 cyanide molecules, cyanide ligands. So compounds having similar formula, molecular formula. Composition is same. 1 cobalt, 1 chromium, 6 cyanides, 6 ammonia ligands in each case. But arrangement is different. You see, in the first case, this is the one compound. Cationic complex in the cobalt is linked to ammonia ligands. In anionic complex, chromium is linked to cyanide ligands. So ammonia is linked to cobalt, whereas cyanide is linked to chromium in the first example. So coordination, that means groups which are coordinating with the central atom is changing. Okay, in this case, you see, in this case cobalt is linked to ammonia. In this case, cobalt is linked to cyanides. Okay, in this case, chromium is linked to bind with the cyanides. In this case, chromium is linked to ammonia. So that's why we define coordination isomerism. So compounds having similar composition or molecular formula, but difference in properties due to difference in coordinating ligands with the same metal atom or ion. You see, you can write this this way. This is a one compound, this is the other compound of similar molecular formula. So you see, the name of the compound is IUPAC name. Can you try to give the IUPAC name? First, you have to tell the name of the cation followed by anion. It is anion, so it is a -6 charge is there. That's why cobalt +3 and chromium also +3. Okay, so the name of the compound is You see, hexamine cobalt 3, hexacyanidochromate 3. That's all. This is the name of the compound. So in this case, we see, observe carefully. We see in this case, we see, observe carefully. Cobalt is linked to ammonia ligands. Chromium linked to cyanide ligands. Coming to this case, name is also changing. First, you have to tell the cationic name. Okay, hexaamine chromium, hexacyanidocobalt 3. So hexaaminochromium 3, hexacyanidocobalt 3, the name of the compound. So name also changing. Compound name, different names, different compounds. Okay, in this case, chromium is linked to ammonia. In this case, chromium is linked to cyanide. In this case, cobalt linked to ammonia. In this case, cobalt is linked to cyanides. So in this case, cobalt in cationic complex. In this case, cobalt in anionic complex. That's why you are telling us cobaltate. In this case, you are telling chromate, chromium in anionic complex. So what is changing? Even though these two compounds having similar molecular formula, but the ligands are changing, the coordinating ligands are changing in these compounds. That's why isomerism is existing. The difference in properties existing. So this is a coordination isomerism. In coordination isomerism, what happens? In coordination isomerism, compounds having similar formula, coordinating ligands changes. Due to difference in coordinating ligand with central atom, properties are changing. That's why these are called coordination isomers. That's all. Next, linkage isomerism. So it is also one type of structural isomerism. So in the name itself, it is understood, linkage. So compounds with a similar formula, similar molecular formula, difference in properties due to different in linkage with the same similar some ligand. Ligands are changing. So this generally we observe this isomerism in SCN thiocyanates and cyanates. Okay, you see SCN or NCS, both are having same, and that means different ligands with same formula. Okay, this is also one more example for, actually this is the example. This we observe this isomerism in embedded ligands in general. If you observe carefully, a ligand which is having two electron pairs, lone pairs, but it is capable of donating only one pair. If it is donated from one atom, we have one type of linkage. In the same molecule is donating, coordinating with another atom in a similar same ligand, same group, we can expect a different type of coordination bond. That's why link is changing. Bonding from different atom, the bonding from atom is changing. So that's why it is called linkage isomerism. Generally, we observe this type of isomerism in only some compounds only, SCN or NCS or nitro or nitrito. The compounds with this type of isomer, this, okay, this is called linkage isomerism. So having same molecular formula, different in properties due to linkage in ligand. That's called linkage isomerism. You see an example. So this is a two pair of compounds. This compound, in this compound NO2, both are having NO2 groups, but this is a linked O, cobalt with O. In this compound, NO, this group is linked to central metal atom with O, whereas in the same similar compound, similar molecular formula, but this in this case, this nitro group is linking to central metal atom cobalt with nitrogen. So cobalt and nitrogen bond is there in the second example, in the second molecule, whereas the first molecule, cobalt oxygen bond is there. So that's why it is a nitrito, it is nitro. So there is a difference in ligands. That's why linkage is changing. But having same formula, ligands also same formula, but linkaging with the atom is different. That's why it is called linkage isomerism. So the second example, you see this in this compound, SCN is linking with nitrogen. Cobalt nitrogen bond is there. In this compound, we have cobalt sulfur bond. So thiocyanato, CC, SCN. This is also electron pair. It is also electron pair. It is bonding from here. We can say N, thiocyanato N. Otherwise, it is bonding from here. We can say thiocyanato S. So S, in one case it is linking with sulfur, in the other case it is linking with nitrogen. So coordinating group atom in a ligand is changing. That's why they are called M-bidentate ligands. So this is called linkage isomerism. So isomers which are having same molecular formula but differing in properties due to different in linkage with an atom in a ligand which is having same formula. So this SN, SCN or NCS both are same formula, but what is changed? Coordinating group is changing. Coordinating group is changing. That's why it is a linkage isomerism. Okay. Then coming to coordination position isomerism. So this type of isomerism occur in polynuclear bridged complexes. That is, complexes having more than one metal atoms. So polynuclear, poly means many. There are so many metal atoms instead of one. So far we discussed one or two. So two or more in these compounds, two or more metal atoms are present in this coordination compounds. It arises due to interchange of ligands between the different metal centers. So coordination position isomerism is changes. So it is arises due to interchange of ligands between different metal atoms. You see, one example is here. You see, they both are having same formula. You see, this is one compound, is two compound. Second isomer. These two are called coordination position isomerism. What is happening in this cobalt? Two cobalts, we have two cobalt atoms. These two cobalts are linking with these ligands, what we call as bridge ligands. So bridge ligands are ligands which are connecting two clusters, two group complex atoms, complex ions. Okay, this is a one group. This is one group. These two groups are linked with these hydroxy groups. So in the nomenclature also we give specific name mu as a prefix to the note. Please specify to specify bridge ligands. Mu, you have to give the mu as a prefix to denote this ligand is a bridge ligand which is linking two or more atoms. So in this case, what is happening? You see, observe carefully. This cobalt is linked to 4 ammonia. In this molecule, in this cluster, cobalt is linked to 2 ammonia and 1 chloride. So that is the difference. In this case, 3 ammonia ligands is linked. In this case, only 2 amine ligands and 1 chloride ligand. So coordination position isomerism. So ligand is changing. So okay, you see in this case what is happening? One Cl2 is there, 1 chloride is shifted to here. So that's why it is a coordination position isomerism. Compounds having similar chemical molecular formula, difference in properties, changing in ligands in a metal cluster. Okay, attached metal ligand attached metal atom is changing. Once again, if you see, observe carefully, in this case cobalt is linked to 2 chloride and negative ligands. In this case we have only 1 Cl and 1 Cl. In this case cobalt linked to 4 ammonia amine molecule ligands. So this is a explanation. In the above ligands, ammonia and Cl are interchanging between the two cobalt atoms. So this is a chlorine is going from here to here. This ammonia molecule is coming to here. You see, what 2 Cl2 is there, only 1 Cl. It is shifted here to here. So that's why Cl is shifting from here to here. Ammonia is shifting from here to here. So that's why exchanging of ligands taking place. That's why in this above isomers, ligands ammonia and Cl are interchanged between two cobalt atoms. So two Cobalt atoms may be same or different. Central atoms may be same or different. That's the difference. So this is a coordination position isomerism. These are called coordination position isomers. So compounds having similar molecular formula, difference in properties due to differ in coordinating ligands with metals. Exchanging of ligands taking place. So in this case, the first case are two amine molecules, two ligand, two chlorides attached to this cobalt. In the second case, this chlorine is shifted from here to here, one ammonia is shifted to here. So in the above isomers, ligands ammonia and chlorides are interchanged. So ammonia is coming from here to here, Cl is going from here to here. Interchanging of ligands. This coordination position isomerism is due to interchanging of ligands between the two metal atoms or three metal atoms, between the metal atoms. That is called coordination position isomerism. This is about structural isomerism. So once again, to discuss what we discussed today is recap of this entire class session. So what is structural isomerism? Definition and classification. So isomerism, two types, structural and stereo. Structural isomerism is of 5 types in our syllabus in the coordination compounds. What are those? Ionization isomerism, hydrate isomerism, linkage isomerism, coordination isomerism, coordination position isomerism. So all these 5 types comes under structural isomerism. So all these 5 types we are explained with one example each. In ionization isomerism, when they dissolve in the compounds dissolved in water or aqueous solution, they give different ions having same formula. In the second case, linkage, number of change in water molecules coordinate to central metal atom. That is hydrate isomerism. Linkage isomerism comes with a similar ligand with different coordinated with different atoms. So coordination isomerism and coordination position. So all these 5 types we have learned with examples. This is today's session. In the next session, we continue the class and complete this chapter. So we have to discuss stereoisomerism. What is stereoisomers? What are stereoisomers? What are geometric isomers? What are optical isomers? We discuss with the examples. Thank you very much. See you in the next class.